Hello, viewers. In today's session, we are going to discuss another important functional equation, right? And here in this session, we are going to discuss this functional equation where we have f of xy is equal to xfy plus yf of x for all values of x and y belonging to the set of positive real numbers. And here an additional condition is also given, that is f of x is differentiable in this interval, that is from 0 to infinity, and we have to find out the function f of x. So here we'll solve this functional equation with the help of derivatives, right? So we'll use the method of partial differentiation to get the value of f of x. So we are given the functional equation, that is f of xy is equal to x f of y plus y f of x for xy greater than 0. And remember, here x and y are not equal to 0. Now we'll differentiate this functional equation both sides partially with respect to x. So differentiating partially both sides with respect to x, will get d by dx of f of xy, and here we have del of del x x fy, and here we have del of del x y f of x. Now here we have f prime of xy, and by chain rule we have to differentiate this product, that is xy. And here when we are differentiating partially with respect to x, then y is treated as constant. So we have simply f of y outside this operator, and we have del by del x of x, and here we can take y in front of this operator, and we have del of del x of f of x. So now here we have f prime of xy, and the derivative of this product xy with respect to x is simply y, because the derivative of x with respect to x is 1, and here this quantity is 1, so we have f of y, and here we have y times f prime of x. So this is our equation number 1. So now this equation 1 is going to be very important in getting the solution of this functional equation. So here what we will do, we'll replace y by x and x by 1, right? So replacing y by x and x by 1, let us see the changes in equation 1. So we have f prime. Now we are replacing x by 1. So here we have 1, and y by x, here we have x for y, and here also we have x, and here we have f of x, and here we have x, and here we have f prime of 1, right? So now we can also write this equation as x f prime of x, and here we have f of x plus x f prime of 1, and let us call this equation as equation number 2. So here we see that we have f prime of 1, that is the derivative of f of x at x is equal to 1. So let us take f prime of 1 as a. So now we can write equation 2 as x f prime of x, and here we have f of x, and here we have ax. For f prime of 1 we have written that is a. So we have now this equation. So now let us call this equation as equation number 3, right? Now let us consider the derivative of f of x over x, right? So we can take the derivative of f of x over x, and then we'll connect this derivative with this equation, right? So here, applying the quotient rule for the derivatives, we have x, then we have f prime of x, and then we have f of x, and the derivative of x is 1, and in the denominator we have x square. So here we have used this result, that is, if u and v are functions of x, then the derivative of this quotient is given by v du over dx minus u dv over dx divided by v square, right? So here, from this equation, we can now write dy dx of f of x over x is equal to x f prime of x minus f of x divided by x square, right? And multiplying this derivative with x square, we have x square d by dx of f of x over x, and taking this term to this side, we have f of x is equal to x f prime of x, right? So now, substituting this value of x f prime of x in equation number 3. So now equation 3 gives us, for x f prime of x, we can write this expression. So we have x square d by dx of f of x over x, and here we have f of x, and here the right hand side is f of x plus ax, where a is f prime of 1. So now we can cancel out these two terms. So we are left with x square d by dx of f of x over x, and here we have ax, right? Now see here, this x and this x get cancelled, because we have already assumed that x and y are not equal to 0. So we can cancel this x with this one. So we are now left with x dy dx of f of x over x is equal to a. Now taking this x to the denominator of a, we have dy dx of f of x over x is equal to a over x. Now integrating both sides with respect to x, right? So here we have dx, and here we have c as the constant of integration. So now in the left hand side, the integral of d by dx of f of x over x is simply f of x over x, and here we have a integral dx over x plus c. So now we can write f of x over x is equal to a, and this is equal to the logarithm of x, and c is the constant of integration. So now let us multiply both sides by x. So we have f of x is equal to ax log of x plus cx, right? So this is our function f of x. So now let us find out the value of this constant of integration c by using some initial condition. So from the given functional equation, we can write, if we take x is equal to 1 and y is equal to 1 in this equation, then we have f of 1 times 1, then we have 1 f of 1, and then we have 1 f of 1. So this is simply f of 1, this is f of 1, and this is also f of 1. So from this equation, we have f of 1 is equal to 2 times f of 1, and solving this equation, we have 2 f of 1, minus f of 1 is equal to 0. So f of 1 is equal to 0, right? So this is an important condition, that is the value of the function at x is equal to 1 is 0. So we'll use this condition to find out the value of the constant of integration. So now taking x is equal to 1 and f of 1 is equal to 0, in this equation we have f of 1, then we have a1, and this is log of 1, and here we have c times 1, right? Now f of 1 is 0, and here we have a, and log of 1 is 0, and here we have c, so this is simply c. So the value of the constant of integration c is 0. Now let us substitute this value of c in this equation. So we have f of x is equal to ax log of x. So this is our required function. So we can also write this function f of x as f prime of 1, because a is f prime of 1, and here we have x log of x. So now let us quickly verify that this function f of x, it satisfies the given functional equation. So let us take this side as the left hand side and this side as the right hand side. So let us first calculate the left hand side. So here we have f of xy. Now f of xy is it can be obtained by replacing x by xy. So here we have a and xy, and here we have log of xy. Now we have a xy, and log of xy can be written with the help of the properties of logarithms, that is log of x plus log of y, right? Now here if we multiply log of x and log of y with a xy, then we have a xy, and here we have log of x, and this is a xy, and this is log of y. So now we can write axy log of x plus axy log of y. So this is our left hand side. Now let us calculate the right hand side. So right hand side is x f of y plus y f of x. Now here we have x f of y can be obtained by replacing x by y. So we have here ay log of y, and then here we have y f of x is ax log of x. So now we can write this term as axy log of y, and here we have axy log of x. So we can write axy log of x, so interchanging these two terms. First we write axy log of x, then we have a xy log of y, which is same as this one, right? So this is equal to the left hand side. So viewers, we can see that this function f of x, which is ax log of x, it satisfies this functional equation. Now let us closely look at this function f of x is equal to ax log of x. Now see, the domain of this function must be the interval that is 0 to infinity, because here we cannot have x is equal to 0. So x is not equal to 0, and moreover the domain is from 0 to infinity, so the negative values of x are also not allowed here, because the logarithms of negative numbers are not allowed in the set of real numbers, right? So the domain must be this interval, that is 0 to infinity.